Welcome to this lesson on arrays. After viewing this lesson, you should be able to declare and initialize one-dimensional and two-dimensional arrays, store and access data in an array, determine the number of array elements and the highest subscript, use loops to traverse or walk an array, compute the total and average of an array's contents, find the highest value in an array, sort a one-dimensional array, and search an array. In this lesson, we introduce a new data type, arrays. Now, you may be asking yourself, hey, we looked at data types at the very beginning of class, and we learned about integers and strings and decimal data types and the other types, Boolean and so forth. Why did we wait so many weeks, so many lessons before talking about just another data type? Well, the reason primarily that we defer talking about the array data type until several lessons into a beginning programming course is that we really need to learn to use loops before we can work meaningfully with arrays. And the reason is that arrays are not only data types, they are also structures. In this case, they're like an ordered list. And so we can have a list or a collection of things stored in an array, and we intrinsically number those things. We call it an index. So if we have a list of the members of the Monkeys band, we have Peter at index 0 and Mike at 1 and Mickey at 2 and Davy at 3. And so we can use this numeric index to reference who we're talking about. So Monkeys 2 is Mickey and Monkeys 3 is Davy. Also note that we're not starting counting with natural numbers. We start counting with 0 when we're talking about arrays. And so an array of size 4 actually starts with 0, 1, 2, 3. So it has more than the 3 elements, 1, 2, 3. Remember, 0 also counts. Okay, so once we have an index like that, we could walk through and reference each of the members of the monkeys array by saying, for I equals 0 to 3, output monkeys number 0, monkeys number 1, monkeys number 2, monkeys number I. So if I is the index that is replacing that. And so that is why we wait to work with arrays. So we've already mastered loops and can use those in conjunction with it. Now, simple arrays are one dimension, and so here they come walking down the street all in a line. That's a one-dimensional array, and Peter, then Mike, then Mickey, and Davy. And we could look at them in reverse order and say Mickey precedes Davy, and Mike precedes Mickey, and Peter precedes Mike. So walk it forward or backwards. We're one dimension, all in a column, as it were. Okay. When we have multiple relationships that we want to keep track of or multiple complexities in the data, then a multi-dimensional array is appropriate. And so this is an example of a two-dimensional array. It has rows going across and it has columns going down, and I've used the America's Favorite Family, the Brady's, for that. And so again, we start counting 0, 1, 2 are the columns, 0, 1, 2 are the rows. The convention is we typically reference rows by and then columns, but it can be done just the other way around just as accurately. It's just you need to follow consistent practice. But we'll reference rows before columns to be consistent with standard practice. And so here we see that row 0, column 0 is Marcia, and row 0, column 1 is Mom, and row 0, column 2 is Greg, and so on. And so, again, these could have been expressed as a one-dimensional array for this collection, but what's interesting is that when we do this in 2 dimensions, now we can talk about not only Peter is followed by Mike, is followed by Mickey, is followed by Davy. We could talk about Mom following Marcia, or Jan being below Marcia, 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 Marcia. And so we can have Alice at the center, or we could say Alice is to Peter's left and to Jan's right and below Mom and so forth. So we can have a lot of richness once we have dimensionality that we can express here, or if we have multiple aspects of data, additional dimensions are useful. So are there dimensions between one dimension and two dimension? Yeah, you can imagine that we could stack the Brady's into a three-dimensional cube, and so that would be a three-dimensional array. And are higher dimensions possible? Yes, we certainly can make higher dimension arrays. It's rare that we would have a program that's so complex that we need dimensionality beyond about 3 or maybe 4 dimensions. Also beyond 3 dimensions when we get into the cube. So we're using three-dimensional space. Anything beyond that is very difficult to conceptualize visually because we process, so we live in a three-dimensional world and we process things dimensionally. We talk about the fourth dimension as time and change over time and that kind of stuff, but it really gets rather complex to visualize. So fortunately, we aren't going to, in this class, going to need to visualize that kind of stuff, and rarely, if ever, are we going to need to work with higher dimensions than a two-dimensional or possibly three-dimensional array, except some very esoteric, usually highly scientific or math functions. Graphics and gaming that uses a lot of graphics rendering can use four-dimensional space, and we use mathematical concepts such as quaternions and whatnot, but that's way beyond the scope of what we need to talk about. Okay, so obviously we can have these arrays declared as, even though the array itself is a data type, it's a data type of another data type. So we have arrays of string, so it stores the names. So both monkeys and Brady's are arrays of strings, but we can also have arrays of integers. We could have arrays of double precision numbers or arrays of decimal. We could have arrays of Booleans. We could have arrays of virtually any other data type. And for that matter, once we start to learn object-oriented programming and make more complex objects, we can have arrays of different object types as well. Okay, so it's very useful, both a data type and a structure, and the structure because, of course, we now have multiple things stored in it. That's kind of a new concept. All of our variables until now have been single valued, and the array variables are going to hold multiple things. And the way I like to think of it is, I remember being a kid having a marble collection, and once I got enough marbles that it was hard to hold them all in one hand at a time, I was dropping my marbles. And so you can probably guess your professor lost his marbles long ago. Okay, but if you don't want to lose your marbles as a programmer, it's really handy to have something like an array that can hold a collection or can structure numerous items of data into one thing. So if you think about it, imagine for a moment that we had to reference all of the Brady's by declaring individual variables. I mean, we might do it systematically and call Marcia Brady 1 and Mom Brady 2 and Greg Brady 3, Brady 4, Brady 5, Brady 6, Brady 7, Brady 8, Brady 9. But any relationship between them, there's no intrinsic relationship between Brady 9 and Brady 1, that kind of thing. So whereas with the array, we have the order and the sequence of the collection, and we can also systematically walk through them. All we have to do, as I mentioned, is to increment that counter, that index for the array. And we're going to see how that's done in upcoming lessons. For now, let's focus on how we can initialize it. And I've shown it right here on the as a label in my interface design. So we declare a variable with dim or dimension, and now it kind of makes sense that you have arrays. There can be dimension to them. So we're going to dimension this array as monkeys, and notice that I have used parentheses. That's what denotes this string variable monkeys as a collection or as an array. So dim monkeys parentheses as string, and at this time I'm also initializing the array. So we're putting right into it Peter, Mike, Mickey, Davy as individual elements of the array. Similarly, we're doing the same thing here, and notice I've kind of broken this line into 3 so you can see that it visually represents the way the array is. So here's our first row, here's our second row, Jan, Alice, Peter. Our third row, Cindy, Dad, Bobby. And each one of those is nested inside another set of curly braces. And the whole thing in a master set of curly braces. And that's, so it says, this is my first row. These are the individual elements of the row, second row, third row. And there we are. So let's take a look at this code running for a second. And we're not going to worry too much about how it works, but this can help us to understand and visualize better what we're doing. So Peter is 0, Mike is 1, Mickey is 2, Davy is 3, and I've hooked this up, and I'll show you an advanced lesson about this new control. This is a numeric up-down control. It's sort of a combo between a text box where we can put in numbers and a scroll bar that automatically increments. So we can also limit the maximum, in this case, to 3 and the minimum to 0. And as that scrolls up, it walks through the array. So the index at, if I come in here and put in 1, index 1 is Mike. Okay, so we're just walking up and down through the array, back and forth, Peter, Mike, Mickey, Davy. And we can also do the same thing here. In this case, I'm scrolling, and I have two parts of the index. I have the row and the column. So if I were to go, let's see, if I wanted Alice, I could manually say 1, 1, and that would find Alice. If I back that off to 0, 1, it's Mom. If I back it up on the other side, so the column, 0, 0 is Marcia. Max it out at 2, 2, and it's Bobby. Okay, so we can walk up and down and back and forth and across, and even diagonally if I do them one at a time, across the grid, across the array. Okay, so play with that. Look at the video a couple times if it's not making sense to you. But see, I've got it's almost like a graph or a grid coordinate system. Marcia is at 0, 0. Alice at 1, 1, Bobby at 2, 2. Over here at 2, 0 is Cindy, 1, 1 to Alice, and 0, 2, 2 to Greg. So again, that's in the 0 row, the number 2 column. And the column, of course, you say, well, gee, wait, that's the third column. Remember, we start counting at 0, so 0, 1, 2. Okay, let's go ahead and break this and see a little bit about that code and the initialization, because in this lesson, that's what we're focused on, is just how do we get this thing initialized. And so here it is in the actual code. And so I am declaring monkeys. Now, I didn't specify a particular size for this array. There's no number here in this parentheses, it's empty. And the reason is because I'm going to, in the same line I'm declaring it, I'm also initializing it by list. Okay, when I initialize it by list, there are 1, 2, 3, 4 items, 0 through 3, 4 items. So this is going to initialize this to a size of 4 items, which, remember, because we started counting at 0, I would put a 3 in there to initialize it to 4 items. That's a little bit strange. It's non-standard. It's different than most other programming languages, but there are reasons for it that come out of the history of VB. And so this would be declared as 3 if I wanted to not initialize it with any values at this time. And we'll see that in just a second here. So same thing for the Brady's. I've got Marcia, Mom, Greg in the first row. So the element 0, 0, element 0, 1, 0, 2, and then on the second row, so it'd be 1, 0, 1, 1, 1, 1, 2, and so forth. Okay, so that's how we're initializing the array there. Now, it isn't necessary to put your data in at the time you initialize the array. Let's take a look at another way we could do that. We could comment this all out. Okay, And now the problem is we need to tell it how big to make those arrays. So in this case, we have 4 items. We're going to declare it 3. So one less than the initialization. As a matter of fact, I think we could just go ahead and comment this whole thing out because I've got it here. So here we've declared the size but not put anything in. So we'll have empty strings initialized for all of them at this point with no data. Now, it's also possible to declare these without specifying the size. Those are known as dynamic arrays, and we'll learn more about those later. And so I'm going to postpone talking about how to initialize dynamic arrays. But I do want to mention this, and that is it is far more efficient and your code will run more efficiently, meaning it'll do more in fewer clock cycles if we use a static assignment of the arrays. So if we can know the size or the maximum size we will need for the array ahead of time, it's better to go ahead and put those numbers in, because then right away at the time that the program loads, that amount of memory for that number of elements in your array of that data type is set aside. If we don't do that, there's a lot more overhead that the runtime system is going to have to do to dynamically resize the arrays, or what we call redimensioning the arrays. And that can be quite inefficient, and it can slow things down, and it can be wasteful of memory and system resources. So we try and avoid dynamic arrays, except of course where they are really necessary. So something to remember when working with arrays from a standpoint of efficiency. All right, so we've got these elements declared, but if we run it right now, remember, we aren't populating the data. Let's see what happens. So if we say go to 1, I'm getting nothing. I'm getting empty strings. It's running, it's not failing, but it's not showing me anything because the array is empty. And we could set a breakpoint and actually see that that's the case. So let's do this. Let's take let's take the monkeys, and let's just set a breakpoint so that we can see this thing operating whenever that routine is called. So we say go, the routine gets called, and let's add to our variable watch list monkeys. And notice the tree structured list here. We can expand it out. And here are the elements of the array, 0, 1, 2, 3. And the value is nothing, nothing, nothing. And of course, that's because we didn't assign any value to it. So we need to initialize it. We learned we could initialize it by actually providing the list when the structure, when the array is first declared. What's the alternative? Well, let's go ahead and we'll do this in the form load event. So let's expand out the form load event. And I've got this commented out here. So I'm going to take this and uncomment all those lines of code. And now monkeys, and remember I said this is called the index. So monkeys 0, which is the first element, is going to be set to Peter, and monkeys 1 to Mike, and monkeys 2 to Mickey, and monkeys 3 is Davy. So real quickly, what is the third monkey? Look at monkeys 2, not monkey 3, because the third monkey, remember we start counting at 0. That's going to throw you. And it's always as unpleasant as a programmer as if you were walking up or down a flight of stairs and find out there's either one more stair or one less stair than you thought there was. Ouch. So don't get caught by that. Remember to start counting at 0. So the third monkey is Mickey. So now at compile time, we create the empty but static variables. So they're full size, but they are empty. And then when the form loads at runtime, then the values are assigned here. So this is the alternative way of initializing the variables, the arrays. the array variables to have the values that we want in them. So let's go ahead and see that. Okay, and so now we still got that breakpoint set. So I'm going to go ahead and clear it until it continue the run. And now 1 is Mike, Mickey, Davey, and all the way back to Peter. And same thing, we're working now correctly on both sides. So we've reinitialized that content. Okay, and so let's take a look at one other thing that's kind of implied by what we just did. Let's set that that breakpoint back here again on monkeys, and let's monkey around. Okay, and so monkeys, if we expand it out, we have Peter, Mike, Mickey, and Davey. And so what we'll find in the lesson upcoming, let's take a little look into the future, is if we take monkeys and aside monkeys 1, if you've always wanted to be a monkey, I've always wanted to be a monkey. So if I say monkeys 1 equals John, that is how we assign a new value to the second element. So not the 0 element, which is the first, but the 1th element, which is the second. Monkeys has no value. Where's my watch window? Monkeys. Oh yeah, okay. There we go. So no return value. Okay, yeah, so now it's the monkeys, Peter, John, Mickey, and Davey. So great. So we learned earlier that I lost my marbles. Now you know that the professor is a monkey as well. So there you are. All right, let's leave that here for this lesson. Now that we've seen how to initialize and declare arrays, let's explore how we access the elements of an array. So back in our sample program, I've got a little button I've just called the Go button. And let's go take a look at the code I have for that. It doesn't actually do much. There's no output here. We're just declaring and initializing a one-dimensional array, and this time I've done it as an integer type, and a two-dimensional array. So this is going to be everybody's favorite Beverly Hills zip code 91210, and this is going to be just a sort of a tic-tac-toe pattern. 987654321 is what it's going to look like in 2 dimensions. Okay, so let's see, once the array is up and running, how can we get data from it and send data to it? How do we make changes in that? So let's go ahead and run our code, and we'll hit the Go button, and it will run down to this breakpoint. And I've already added to our variable watch window my array and my 2D array. So if we expand that out, we can see that the elements 0, 1, 2, 3, 4 are 9, 1, 2, 1, 0. Okay. All right, so if we wanted to modify that, let's see, can I undock the immediate window and separate it from the watch window? Is there a way to do that? I'm not seeing, let's see. If I float that, nope, can't break it out. There we go. Okay, so we've got the immediate window here, and we've got my watch windows, which is what we're really interested in up here. Okay, so in order to change the elements 0, 1, 2, 3, 4, I refer to them as simply my array and then 0, 1, 2, 3, 4. So which one shall we change? Shall we change, let's change the 2 to a 4. So that is element, the index 2. So we put a 2 here, and we would like to change that to have the value 4, and press enter, and there it is. That value has not now been changed. Okay, and so if we wanted to get data out of this, if we wanted to say what is the value of the third element, I could say, and in the immediate window the question mark means print, and I could say print my array. And which one did we want? I've forgotten. So let's say we want to output the value of index 3. We say index 3, and it says the value is 1. Is that correct? Well, yes, it was. And we can also do both of these at the same time. So we could say that my array 2 is equal to my array 3. So my array 3 is 1, and that's going to take the 1, and it's going to make my array 2 equal 1. So it should be at 91110 when we finish this. Let's see if that's what happens. 91110. Yep, works beautifully. Okay, so great. On the one-dimensional array, does it work the same way on the two-dimensional array? Yeah, with just the notational differences, it does. So this says 987654321. Let's say that we wanted to change that 1 to 100. Well, that is index 22. Okay, so if we say my 2D array 22 equals 100, bam, it's changed. And we can output it the exact same way. So we could say that we want to output or print my 2D array element 2, and we get a result of 100. And just for completeness, to show that we could do the same sort of thing here, we could take my 2D array element 0, 0, 0, 0, and make it equal to my 2D array element 2, 2, and press enter. And when we do that, the 100 here, we should copy that value. That stays there, but it will replace the 9 with 100. Let's see if that's what happens. And yep, indeed, that is exactly what happens. So accessing the arrays, that's where that index, that offset comes in handy, and really nifty and useful to have arrays that are ordered that way, so that we can have a whole collection of things, and we can order them if they need to be ordered. We can do other things that we'll see in the coming lessons that are fun, such as getting the total of the array, or the maximum value, the smallest value. We could find the average, almost anything that's useful. So we'll see in the coming programs all the wonderful things we can start to do with arrays. It opens up a whole new world of power to our programming. Now let's look at how we can determine the number of array elements in an array, and also the highest and lowest subscript assigned to an array. So you might be asking, well, why would I want to do that? I created the array. I know how big it is. Well, a couple reasons. One is, if we're going to reference those sizes in code, you don't want to really hard code those numbers, make them, a permanent absolute assignment if you're referencing it, because you may come back and later on change your code so that the array has a different dimension, and then what you would have a dependency in your code elsewhere that references, if it was a single dimension array of length 5, you might reference 5. Well, if you come back and change it in the definition of the array, Now you've got 5 referencing it, and maybe now it's 10. So you've got 2 places to maintain it in the code, and that's a poor idea. But maybe a more compelling reason is soon we're going to learn about dynamic arrays, arrays that under program control might be changed in size and made larger, typically larger. Not often we do it smaller, but either way, the size is going to change, and so we might not know at design time how large an array is at some particular time in the program's execution, and we may need to do some other work to accommodate that. So you need to know, you be able to programmatically retrieve the size of the array, or what is the highest subscript in that. So let's create some sample arrays to play with and explore this. So let's go back to our sample code, and here on the Go button, click Event. I've got just a standard decimal variable result hanging out in case I need to use it for something. And I've got my array currently defined and initialized in the same line. It's got our Beverly Hills zip code 91210 are the 5 elements of this array. And then I've got a 2-dimensional array. This one has 12 elements, so it's got 1, 2, 3, 4 rows of 3 elements. So 4 by 3 is 12 elements. And I've also got another array that's a string that I'm not initializing at once, and I'm putting 2 elements into the 5 that the array can allow. So again, array 4 means it's a size of 5 because it's 0, 1, 2, 3, 4. So don't get tripped up by that. All right, so I've got a breakpoint here so that we can, through the immediate window, or I think we'll probably do most of our work here through the variable watch window, we can use some dynamic expressions to look at values and figure out how to manipulate using some of the array properties to find the number of elements and also the highest and lowest subscript in an array. So let's go ahead and start our code. And we'll fire that off. And again, it doesn't have any interaction with the screen, no output. So aside from using it in debug mode, this code isn't very interesting, but it's very useful here. So first of all, let's take a look at my array, which is 1, 2, 3, 4, 5 elements long. So it's an array 4, so 5 elements. And how might we programmatically determine that the length of the array is 5? Well, arrays are actually under VB fairly sophisticated objects, and they have a whole collection of methods we can use, and length happens to be one of them. So if I say my array dot length, that will return, the length method will return the length of the array, and we see that it is 5. So again, we would declare that if we were declaring it as a static array without initializing it, we would declare it as an array 4, which means 0 through 4, which is 5 elements. Okay, so that's a quick and dirty way to get the length of the array. Now, does that work for 2-dimensional arrays? So when we have 4 rows and 3 columns, what is it going to return? Best way to learn this stuff is to actually try it. So let's try an experiment. Does it return 4? Does it return 3? Or maybe 4 times 3, the total length of the array is 12 elements. So it unwinds it and gives us the count as if it was just a linear or 1-dimensional array. Let's see what happens. So let's try my 2D array dot length. And indeed, it gives us 12. So we can use that expression in our code to get either a 1-dimensional or 2-dimensional or multi-dimensional array, the total length. That's really the total count of elements in the array. So if I had a 2-dimensional array of measure 4 by 3, 4 by 3 is 12. If I had a 3-dimensional array of 4 by 3 by 4, 4 by 3 is 12 by 4 would be 48. And so we would get the total length there. And we're going to leave higher dimensionality kind of for later or as something you can explore independently. 2 dimensions about as far as we need to go for this lesson. All right, so the length is fine. What if I needed to understand the size of the dimensions of these? Well, in the case of the one-dimensional array, that's really not going to be different. It's going to tell us the highest subscript is 4 because it's 0 through 4. But what's that going to be in a two-dimensional array? Well, let's explore that and see how we find that. So first, let's start small. What is the lower bound of the array? In these with these arrays, it should always be 0. But let's find out. So one of the methods that is available on the array object is the lower bound. So myArray.lBound oops. Looking for it. Get lower bound is the method. Lbound would be the property. So get lower bound. Oh, let's try it in the immediate window. I don't know why it's fighting me. All right, so I don't know if it should be able to express the property as well as maybe the method can't be expressed in the watch window. Okay, so let's try it here in the immediate window. So print my array oh, did I perhaps not have no, my array is there. So print my array dot okay. Always good to see the professor is human. So I'm going to leave this in the video so you see the kind of mistakes I'm making and how we deal with it. So I'm going to come back to the code. I stopped the run and I'm going to say result equals my array dot. Now I can look at the properties and we're looking for the lower bound property. I see. So the method wants get lower bound and the dimension, which is going to be the first dimension, and get the index of the first element, and a zero-based dimensioned array whose starting index needs to be determined. So if we get the lower bound of 1, I thought we could also do that as just a call to low bound, L bound. Am I misremembering that? No, it looks like it's get upper bound and get lower bound. So let's move a breakpoint up here. And let's get the lower bound and then we'll get upper bound. And give that a run. And go. And now let's go back over to our watch point and what is result at this point? And lower bound is 0. And let's get the upper bound and we do that if we hit F10, we'll step forward and run this next line. And the upper bound is 4. Okay, so that makes sense. So the upper bound on dimension 0 is 4, which means 0 through 4, it's going to have 5 elements, which we already discovered when we expressed the length. Let's go back and see if we can do this now. If I could have done that directly, my array dot get upper bound. I probably just didn't. Yeah, I didn't put the parameter in. And now the debugger, now the watch window likes it. Okay, so good. We learned something. All right, so we have the upper bound, lower bound, and we provide the dimension, and that kind of gives us a hint what we're likely to have to do if we wanted to get the dimension or the size of individual dimensions on a multidimensional array. So let's try that and see how that works. So if I try my 2D array dot get upper bound, and let's see, we'd like to get the upper bound of the first dimension, and that says 3. And let's also get my 2D array get upper bound of the second dimension, which of course is the first dimension. We start at 0. So 0 is the first, 1 is the second. And we see 3 and 2. And you're like, wait, what gives? I thought this was a 4x3 array. It is a 4x3. So remember, the upper bound is 3. The lower bound on that dimension is going to be 0. 0 through 3 is 4 elements. 0 to 2 is 3 elements. So it is a 4x3 array. So if we were doing get length, it would give us the 12. If we wanted to calculate that by multiplying dimensionality, we need to, if we were a 0-based array, we need to start by adding 1. So 3 plus 1 is 4 times the quantity of 2 plus 1 is 3. 4 times 3 is 12, and we'll come up with the 12 elements in our multidimensional array. So here's how we can get the sizes of that. And so we can see the maximum number of elements in an array and the maximum elements in one dimension. Okay. What's a little bit trickier is, let's say, for example, we want to know how many elements in an array are used. Okay, so the size of the array is different from the number of elements that are used in the array. And what does an array look like when not all the elements are used? So I'm just going to delete what's out of our watch window now. And let's take a look at, we've got another partially filled array here in this another array as string, and I've put in alpha and beta out of 5 elements, 0 through 4. So let's take a look at what this looks like. So another array. So here's the another array object, and the length is 5 and type is string. And remember, we can use the tree view. We can expand it out and see the elements. And so here's alpha, here's beta, and then it's something called nothing. Okay, it's the empty string. Okay, so one of the ways we could tell, even though we have an array of size 5, if we want to know how many elements we've used, assuming that we start filling the array from the start, and we don't have to, we could put things in different elements. We could put something at the end without having anything in the end, right? But assuming that we're filling this in order, we could take the strategy of start at the beginning and look for a string of nothing. When you find a string of nothing, then you know that if we count, so if I count 1, 2, 3, I know that nothing was found on the third element, so there are 2 items stored in the array. Now that strategy works for string arrays. What about numeric arrays? Because is there the equivalent, the numeric equivalent of nothing? Is the idea that we learned maybe in a database class of null, does that work in VB with numeric arrays? Well, let's take a look. So I'm going to stop this run. And let's come back here and let's change the declaration of my array. And let's declare it but not put anything in it. And then we'll look and see what does the compiler put in it. What happens to it if we don't have any variable values assigned to the elements. So run that again, go, and let's take a look at my array. And still length of 5. And did I grab the right one? Yeah. There we go. Now it's updated. It's integer. Threw me because it looked like it said string a minute ago. All right. Oh, this is not empty. This has the value 0. Well, what if 0 is a valid value? Well, one of the ways we could find out, how many elements have been used, we could pre-initialize. Let's say when we first created this array, that we filled it with some value that we will never ever use for our particular needs. So if we put in -999 and to every unused piece, every unused element, what we could do here is we could say, hey, is this value -999? No, then add 1 to the number of used elements. This one, nope, 2. This one, nope, 3. This one, yep, okay. So we would know we have 1, 2, 3 elements that are stored in the array that's 5 elements long. So the alternative would be we could keep track of the things we've stored in, or number of things we've stored in an array with an external variable. But this way we could kind of intrinsically always look and check and see, kind of more advanced and esoteric than perhaps what we need to explore the upper bound, lower bound, and length properties of the array, but I think worth taking a moment to talk about. Now let's see how we can use a loop structure in order to traverse or walk an array. And this is really the reason that we've kind of held off until now, after we've studied loops, to really start introducing the array structure, because arrays really are much easier to deal with when we have to traverse them, which we do frequently, when we have the loop structure to help us do that. All right, so let's go ahead and look at how I've modified the code. And here I've set up a region with some code that's all commented out for walking the array. And so we're going to use one of the arrays that we've already become familiar with. So we have the my 2D array, and if I show you how to walk a 2D array, it'll actually be pretty obvious how to do it with a one-dimensional array, and also how to extend that if you're dealing with multi-dimensional arrays beyond 2 dimensions, so 3 dimensions, 4 dimensions, and so forth. Okay, so here is a hard-coded approach. It's kind of foolish because, again, if we hard-code the parameters, so we're going to walk this array, which currently in our code is a 4x3 array, so 0 to 3 and 0 to 2 when we're talking about rows and columns. So 0 to 3 is 4, and 0 to 2 is 3 elements, so a 4x3 array. So what we're going to do is for each row, and within that, for each column, we're going to traverse it. So we traverse each row element by element and return each element in the row, and then we increment and go to the next row, moving down the column. Okay, so that's basically what's happening here. And what I'm going to do here is simply print whatever the index is for I and j. And indeed, that'll work. Let's go ahead and we'll set a, let's run it first without a breakpoint set. We'll set the breakpoint at the end of the subroutine and just see quickly what the output is, and then we'll break it down with the debugger and see it incrementally. Okay, so we run our code, hit the go button, and our, let's see, I didn't clear this before, so let's clear that and rerun it again. So there's no artifacts there, so we see what our output is. Okay, so it walks down 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, shows each element in that array, which is what we'd expect. Now let's go ahead and modify the code and put in, actually we'll modify the code, we're going to modify the environment. Let's put in a breakpoint so that we can see that code in action. So let's start at the very first time we start to walk that array in the loop and go. And let's see here. Let's look at the watch window. And in the watch window, let's keep an eye on the value of I and the value of J. And let's also take a look at the contents of my 2D array ijth element. Okay. All right. So let's go ahead and run that again. And go. Okay. So at the beginning of our outer loop, before we've done any iterations on either loop, both the values are 0, 0 to 3, 0 to 2, as we'd expect. And let's hit F10 and step through this. We step in. Now we're going to start the inner loop. So while I is 0, J is 0, and so 0, 0 is, and let's debug the output, or print the output. And so it's going to go ahead and output that to our immediate window. So it's output the value 12. So we're starting the second run down here. I should have cleared that screen. I'll do it now. So the next one will be 11. And then let's go ahead and hit F10. And now we're still on the same 0th row, and we're stepping to the next element. And the output is 11 and 10 and so on. Let's go back and see what's happening in our watch window. And I'm not getting an update here. My 2D array and maybe currently out of scope. Let me run that again. There we go. Now it's updating, and we can see it walking down. The rows and the columns until we reach the end. And again, here's our output, the 12 we erased, 11, 10, 9, 8. So it's walked down each element in the row and then moves down the column to the next row and walks down that row down to the next row, walks down that row, and outputs as we go. Okay, so that's pretty straightforward. And we understand that. But again, here's why this is a bad idea, is if I go up and were to redimension this, let's say I came in and edited the initialization and added another row, 15, 14, 13. So I've added another row to it, but here I'm only walking, I haven't updated the dimension. This part of my code did not magically or automatically get updated to handle the fact that there's another row there. So that's going to be a problem. And I'll have to encounter that error, and I may not catch it in testing if I'm not careful enough. And so we turn that code over to our users, and they start using it. And then as soon as they get to that point, they're going to start to have errors. It's going to have, actually, we're not going to walk the entire array. We're never going to get some of the data back. That would be bad. A logic error, but not necessarily one that causes the program to crash. Okay, so what's a better approach for that? Well, let's take a look. I'm going to clear that breakpoint, and let's go ahead and comment that all back out. And what would be a slightly smarter way to do this? Well, we learned about the get lower bound and get upper bound property or method. And so let's go ahead and use that. So here, no matter how I might resize that array and change my code, it's doing dynamic determination on the upper and lower bounds. And so this code doesn't care if I make any changes, and we'll prove that. Okay, so let's run this code and see that it works as is. So let's, oh, this should remain a comment. That's what it's complaining about. Sorry about that. And we run this code, and let's look at our immediate window, and it's run down 12 to 1. Let's clear this out and tell it to continue, and let's run it again. And now we see in the immediate window 12 through 1, and that worked handily. Okay, I'm not going to take the time to put a breakpoint in and step through individually here because it's exactly the same order as the last detailed break that we did, except that instead of using hard-coded boundaries of 0 and 3 and 0 and 2 for the outer and inner loop, it is dynamically determining those values. Well, let's go ahead and do this much. Let's stop this, and let's put a breakpoint in here, and let's just look at this as a watch. So let's run that, and let's clear our window again, and let's step in a little bit until we get it kind of interesting, and then come over to our watch window, and let's see what that value is for the current bounds. Let's see. So we're actually J. So we're now at 3, 3, where we've stopped. And notice by putting the break on the inner loop, did you notice that it was breaking only after every third element? So after it's completed the row. And so we run it again, let it continue, bam, and gets the last 3. So let's see that again. Let me clear this and continue, go, and continue. Boom. Because we've only got the breakpoint on the inner loop, the outer loop continues to run, so it runs until it gets to the break every third element. 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so much smarter way to write the code. Can we do better than that? Yes, there is a way to do better than that, and that is with a new for clause that we haven't worked with too much before. You may have seen it in sort of the sneak previews and extra for expert stuff that I've shown in some of the lessons. And this will work with basically any object that works like a collection. If it has can be interpreted as a collection, the for each loop will work with it. And so we're going to do this now as a for each. So let's go ahead and comment this back out, turn it off, and I'll collapse that region. And let's take a look at, typo there, walking the array number 3, and this is, according to my comments, for each loop best of all. Okay, so let's I'm going to use another integer variable. I could reuse I or j, but I don't want to confuse the issue. So I'm going to create a new integer variable called element. And the reason it is an integer variable is because the array that I'm working with stores integer type. So each element of the array is going to have an integer in it. If it was using a different type, a string or what have you, I would declare that as the appropriate type. In this case, it's an integer array, so I'm making integer element. And let's go ahead and uncomment these as well. Okay, so for each element in my 2D array, well, each element, okay, so even though it's a 4 by 3 array, which means there are 12 elements currently, I don't have to walk the rows and then the columns, or if I have higher dimensionality, the X, the Y, the Z dimensions of that. This is almost like it unwinds it and treats it like a linear array. For each element in this whole thing, print that element. Does that actually work? That's kind of crazy, isn't it? Let's give that a try and see if that actually works. So let's run, let it go, and zoom. Let's clear this out and run it again so you see that the immediate window is dynamically being populated. Continue. Run it again. Bam, 12, 11, 10, 9. Wow. And we didn't, in our last step, prove that when we have it dynamic like this, that if we modify our array size without changing any other code, that it works. So let's go ahead and go back and do that. Okay, so without having to change anything in this loop, if I come in here and add another row to this thing, so let's call it 15, 14, 13. Does that actually work without further modification? And there it is. Let's clear this out so you can really see it clearly. Run it again. And yeah, if we scroll up, we can see it started 15, 14, 13, and there are all the elements of the array down to 3, 2, 1. So they are all there. And so that works well, whereas our original naive approach of hard coding the dimensions of the array into our loop would have been broken here if we'd forgotten to update that. I'd have to go ahead and change the number of rows that there are that we're walking from 0 to 3 to 0 to 4. So from 4 to 5 rows. So nifty. Okay. One last thing we want to revisit here that we touched upon in an earlier video, go ahead and comment this out, is what if you are populating an array, you've declared it of a certain size, but you don't have data in the whole thing yet. Now, assuming that we do something sensible like starting at the beginning of the array to populate it and populate each available element as we go, then when we run out of data, we could detect that in a couple different ways. And let's see how we might do that. And I'm going to set a breakpoint right here so we'll have a moment to pause and look at the contents of another array and see how this works. So basically what we're going to do, another array is a string array. And the string array is going to have, when we first initialize it, nothing in it. And if you recall, we declare it as an array 4, so it's a 5-element array, but I only put 2 of the 5 possible elements in there. So in the 0th element, I put in alpha, and in the 1th element, I put in beta, and so it's going to then have 3 more strings that are empty strings, nothing, nothing, nothing. So here, I'm using not exactly a definite loop. This is an indefinite loop, so I'm saying while this condition is true. So while the index I'm currently looking at, starting at 0, and then I'm going to increment it as we go through the loop, starting at 0, as long as the result is not the empty string, the nothing, then I'm going to print the contents. Once I've run out of data, I will stop. Okay, and this is kind of handy. Maybe it's kind of a kludge, kind of a get around, because the array itself doesn't have any way of keeping track of, have you put data in some or all of the elements or not, and where is the last data element if you start putting them in at the start of the array. That's not a feature that the array structure or the array object provides for us automatically, but we could either keep track of it as a separate variable, or we can look at some characteristic in the array. In this case, we're looking for the nothing to find it. So let's run that. Go. Let's come over to the watch window, and let's get rid of these variables we're not interested in, and let's take a look at another array and remember how that was built. So originally it was just an empty array of length 5, so an array 4, which means length 5, and then we put something in the 0 element, we put something in the 1 element, and then there's nothing in the remaining elements. And let's watch how this code is going to work now. Okay, so if I hit F10, while the another array I, whatever index we're looking at, is not nothing, we're going to continue to go. And we're going to print. And so the first element had the value alpha in it. And we increment, so next we're going to look at I as the second element, the value 1, okay, or the index value 1. The contents of that should be beta. And boom, we're printing out beta. And then after that, when it comes up here, remember that in element 0, 1, 2, so the third element, it's going to have nothing. And so it says, while it's not nothing, but it is nothing, so I fall out of the loop and in the subroutine, and I can go ahead and have that continue. Okay, so it only printed while it had data. And again, remember that works pretty nifty for arrays that are strings, because when there's nothing in there, we have the null, or actually an empty string, the nothing, as it were. That doesn't work in VB if we were talking about numeric values. So let's take a look, and here's an array of 5 as integer, my array. Okay, and so just to recall why that wouldn't work as well as our approach with the string, back over here, let's take a look at what the contents of my array, which is a numeric, in this case an integer array, and you look at that, and even though we have not initialized it, VB initializes it so that instead of being a null value or an empty value, it has initialized it to zeros. And 0 could very well, for whatever program we're in, could be a legitimate value. So again, one of the ways we might change that is, say, imagine for a moment that in my program, the value negative, let's say negatives are not allowed. So -1, -1. So we could initialize this variable, this array, to have all -1s, and then you put in actual data. Okay, so these would be the legitimate data, and we could loop through, still legitimate, and then when we find the trigger value, we could say, oh, that array has no more actual data in it. We would know that this value is not a legal value. It's one we put in there to sort of keep track of where we had ended adding to the array. And so that's kind of a sneaky trick for dealing with that. All right, so just to recap, we can walk an array using a loop, and we could walk it. In this case, we've been walking it to read data out of it, to do an output. We could also walk the array in order to input. So I could just as easily have prompted the user to put some value in and recorded that, stored it to that location. And the problem that we see here, this method, kind of naive, hard codes the dimensions of the loop. If you ever change or not the loop, hard codes the dimensions of the array. If you ever change those, this code would have to be updated too. If you make sure you do, well, everything works okay. But why not code a little more defensively so that we don't have dependencies scattered all over the code? So a better way to do that, if we have to code the loop um, using bounds, is to dynamically get the lower and upper bounds for each of the dimensions, the 0 dimension and the 1 dimension. So the x and the y dimensions, if you're thinking about it like a Cartesian graph. And that works pretty well. But there is another way that works even niftier with niftier. Is that a word? It works even niftier with arrays and also works on collections, and that is to take advantage of the for each loop structure. And that is not dimensionally constrained at all. For each looks at it like for every element in the array, however many dimensions you use and whatever complexity, whatever the size of those dimensions, for each is going to work just fine if we address it element by element. The trick here is make sure that we declare the element as the same type of the array. That is not going to change during the run of the program. Whatever the array type is, that's what that array type is for the whole run of that program. So we don't have to worry about that changing. And then finally, what if you have a partially populated array? Where do we find? How do we find where the data ends? Kind of a kludgy solution. One way is if it's strings, look for where the string becomes the empty string. Or secondly, if it's a numeric, we can pre-populate it, pre-initialize the array, and store sort of a flag value in there that wouldn't be used by the program. And so we go through the data until we come to that flag value. We use that as our stop. We know that's where the valid data ends. So one final thought, and that is even in a string, it is possible that some empty strings are legitimate values, in which case we'd have to use a different approach with our different strategy with our string arrays, and again pre-populate it with some value that maybe the word stop or something like that, or some special character that would be used as a flag value if we wanted to allow the empty string to be a legitimate data value for some reason. All right, so that's walking arrays using loops. Two very common tasks we'll need to address in working with arrays are to calculate the sum of the values stored in the array. The other is to determine the average of all the values stored in the array. So let's see how we can do that. There's good news and bad news in this proposition, and that is that if you're dealing with one-dimensional arrays, there is actually some method or some property that will give us the sum pretty quickly. So we're going to work in this example with the one-dimensional array myArray and also my2D array. Let's take a look at how those are currently initialized. So myArray is an integer array containing 91210, and the my2D array is got the values 15 through 1. So if we add up the sum of by hand of my array, 9 plus 1 is 10, and 2 are 12, 1 is 13, and 0 leaves us still at 13. If we wanted the average of that, 1, 2, 3, 4, 5, 13 divided by 5 should give us, 2.6, I believe. Okay, and so use that for a sanity check here, and let's see how this works. So how did I know that this method was out there? Well, I read the manual, but short of that, if we are working with that and we say my array dot, using the dot notation, IntelliSense brings up all the different methods and properties that are available, and we're looking for the total. In this case, total is a synonym word, sum. And so we're looking for the sum. If we click on it, it'll tell us a little bit about it. Computes the sum of a sequence of integer values. A sequence in this case is the entire sequence, unless we tell it otherwise, of the entire array sequence, because we can think of an array as a sequence. So adds them all up and gives it to us. Great, automatic. Let's see how that works. So let's, I'm going to set a breakpoint right there, and let's go ahead and so just before it is to output that, we're going to stop the program and let's run it, go, and over to the immediate window. I'm going to clear it. Great, so now we got the stage set, and if I hit F10, it will step over that and 13, and that's what we expected for the sum. So that's working really slick. Couldn't be easier. Saves us a ton of programming. Okay, and so we go on happily and say, oh, well, now we've got our two-dimensional array. Let's give that a try. Okay, and as you've noticed here, my anticipating the work here, I've got that in there, and as soon as I let that go, it says, wait, squiggly, 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 it's not happy. Sum is not a member of integer multidimensional array. Oh, perhaps it is not. So let's take a look at that. If we try and use that my 2D array, and I press the dot operator, and here are all the possible methods and properties. Maybe I just misunderstood. Maybe I didn't use it properly. Scroll down to sum. Scroll down to sum. Yeah, not finding it. So it's not there. It's not a property that is available. So does that mean we can't ever get the sum of values stored in a 2D array? Well, of course not. We just need to code it. Okay, so let's put this back. And let's get rid of this error by commenting it back out. And waiting in the wings, I have the actual code that will do that to save a little time. So let me uncomment that, and let's walk through how this is going to work. First, I need an accumulator to report the total. So I'm creating an integer, because the sum of integers will always be an integer. So integer arrays, if I'm going to add all those up, that would be the appropriate type, and we'll call it my total. Okay, and then I would like to use that nifty for each loop. So again, I'm declaring an element variable, dim element, and it is an integer array, so I'll make it an integer type. And then I say, for each element in my 2D array, accumulate elements into my total. So my total plus equals element, and you'll remember the plus equals operator. It's worth recapping here. That is exactly the same as if I said my total equals my total plus element, but I can simplify, use shorthand using the plus equal notation, and say my total plus equals element. And when the loop is finished, if I output that, I should get the total of the numbers 1 through 15. Let me put a breakpoint there. Let's see if it works. Run it, go. And so let's clear this immediate window. And I'm getting that, by the way. I'm right-clicking and saying clear all. And then let's go ahead and hit F10 to step into that next one. And there it is, 120. So the sum of the integers 1 through 15 totals 120. That's what we expected. And that's working. Okay, so could we have done exactly the same thing using a for each loop on the one-dimensional array? Sure, we could. But since the property is built in, we're going to go ahead and invoke the property of the one-dimensional array object, and more's the pity that it isn't provided to us by the Microsoft programming gods to do that for us automatically. So we have to provide our own code for two-dimensional or anything higher than one-dimensional. What about averages? Okay, well, again, exploring my array with the dot notation. Oh, look at that. Right there, average. So I can express that as a property. It does exactly as we would expect it to do. So let's go ahead and debug print my array average. And what do we say the average was? 2.6. So let's give that a little run. Let's set a breakpoint here first, right before it. There we go. Now let's give it a little run. Fire it off, and let's clear the window so we don't confuse it. And I don't know why it's complaining about the stack trace. Let's put that away for now. And let's go ahead and hit F10. And there we are, 2.6, the average of the my array, exactly as we anticipated. And let's go ahead and end the run. And that's fine. Let's put that away. Now, if we didn't have the sum function on multidimensional arrays, you pretty intuitively know we're not going to have the average function either. Because if we had, in order to get the average, you would have to have the sum. Because what is the average? The average is the number, or the sum of the elements divided by the number of the elements. And so we hit the dot notation, and using IntelliSense, we go to scroll down to the average, and up, where's average? Not to be found. So can't do it. Okay, so it would have looked like that had it existed. And we'll just make a note for completeness. So the average property is not available for multidimensional arrays. So what do? Well, we'll do it by brute force, of course. Now we'll write the code for it. So what we want to do, strategy-wise, get sum, get count, okay, then average equals sum divided by the count. Right? Well, we know we can get the number of elements, so that'll give us the count. And so what we need is the sum. So let's see, we still got this declaration of element. So I'll tell you what, we'll leave that out. We can go ahead and comment out this piece. We're done with that for the time being. But we're going to leave element, and we're going to leave my total. Actually, we can use that, can't we? Right? So let's actually uncomment that. And so we'll reuse my total. And so if we have the total, which we do, we're just not printing it anymore. Let's say debug. Well, what's the expression? The expression is going to be my total divided by my 2D array dot length. Gives us the number of elements in there, and that is the average. And what was our sum of numbers 1 through 15? It's 120, and there's 15 of them. So 120 divided by 15 should be 8. And let's see if that works. We'll set a breakpoint right here just before it runs and see if we got that right. And go. And right click here and clear all. And F10. And there it is. The average is 8. And maybe we should identify that number. And so let's have a little fun with string handling. And we'll say, so we'll print the average of values in my 2D array is quote, and we'll use the concatenation operator, and then we'll take this whole expression here, and since we're mixing it with strings, we ought to cast it to a string, toString, and now it will be a little prettier. Let's take a look. Go, clear this out, and F10. The average of values in my 2D array is 8, only I squished the 8 together there, so I should have probably put a trailing space right there. Let's break it, rerun it, go. Let's clear that out, and F10. Now it looks nice. The average of values in my 2D array is 8. Very cool. That'll do it for this part of the lesson. We've seen that finding the average value or the total value of elements in an array are two common tasks. Another common task that we will do with arrays is to find the lowest or highest value stored in the array. So let's take a look at how we would approach that task. All right, so let's pop over to our code here, and again, as you come to expect, in one-dimensional arrays, this is a pretty straightforward thing to do. Let's go ahead and collapse the totals and averages. There we go. Okay, so in a one-dimensional array, there is a max function and a min function, and it works just as you've come to expect with the average and the sum functions. I shouldn't call them functions. They're actually object properties. So let's go ahead and set a breakpoint right there and see that running on our 90210 content array. And so of 90210, 9 would be the max and 0 would be the min. And let's see if that works as expected. And go. And let's see, I still had something else in there that's printing. So we didn't disable that print. We probably should turn that off. So we'll just go ahead and hit F10 and keep going. And so here it's going to print the max, 9, and the min, which is 0. And so that was what we expected to have happen. Okay, so that's pretty straightforward. But again, also as we've come to expect, when you come down, so you guessed it, there is no max or min property for multidimensional arrays. So what's our strategy for dealing with that? Have we got any other breakpoints we need to clear? Okay, we'll go ahead and clear those out. All right, so just think this through, even before we look at the code. As a matter of fact, let's pop here so you're not looking at the code. Let's think about this. We have in our array, an array with a whole bunch of contents, and we need to figure out where we can find the lowest and highest numbers in that array. So one way we could do that is to start by comparing all the numbers in the array, one at a time. So if we visit each element of the array, so we traverse or walk the array, which we know how to do, we can look at each number, comparing it to find the lowest and the highest. Comparing it to what? Well, let's think about that for a second. When we start, the first number we encounter is going to be the lowest we've seen so far. It's also going to be the highest we've seen so far. So we could start out setting our low value and our high value equal to whatever the first element of the array is. So if it's a two-dimensional array, that'll be the 0, 0 element. So let's set the low value and the high value to the 0, 0 element, and then let's go through the rest of the array. And what we need to do is simply compare each element in turn. And if we find one that is lower than our last low value or the current low value, we'll replace it. And if we find one that's higher than the current high value, we'll replace it. And when we get to the end and have looked at all of them, whatever we have in our low value and our high value buckets are going to be the lowest value stored in the array and the highest value of the array. Let's think about possible problems. What if there are more than one low value stored, so more than one copy? So we have an array that has, let's say, the value 0 stored in it twice. Well, that's okay, because 0 is equal to 0, so it doesn't matter which 0 we're talking about. 0 is still the lowest value. Same thing for the highest value. If the highest value we happen to have in the array is 1,000, and there's 2 instances or 5 instances, or even the entire array is full of 1,000. As a matter of fact, in that case, not only is it all right that the high value is 1,000, if all the values in the array are 1,000, we would have the weird but perfectly legitimate situation where the low value is equal to the high value, and they'd all be equal to, in this example, 1,000. So let's go ahead and put that in our code. Okay, so I have declared a lowest value and a highest value variable. And those are both going to be integer types simply because that is the data type of the data stored in the array. If it was a decimal, I would make it a decimal. Okay. And then I'm starting out and saying, before I do anything else, go get the value of the 0, 0 element, the first element in the array. And again, I've hard-coded this with my lower bound. You could make a case that what I really ought to do is get the lower bound, so I could express that as my 2D array 0 get lower bound and my 2D array 1 get lower bound in order to get those. I think we're going to be a little cavalier and assume we're safe that all the arrays we're going to be working with start at the 0th element. And that's typically the case. It's kind of esoteric if that's not the situation. Okay, and we're also going to set highest initially to that same value. So whatever we find in the first element of the array, we're going to set that initially to the highest and the lowest, and then we're going to use our handy dandy for each loop. And for each element in the array, in turn, we are going to compare that value to the lowest, and if it happens to be lower than what we previously had marked as the lowest, we're going to replace the lowest with the contents of that element. And the same thing for the highest. We're going to go through each element in turn, and the very first element is what we've tagged as the highest. If we happen to come upon one that's higher, we're going to replace the highest value as the value of the element we found that is higher. And it will go through that, repeating that process for every element in the array, so that by the time we are done, whatever we have stored in the lowest variable and in the highest variable will be the lowest and highest values. And let's go ahead and see that in operation. So we'll run through here and go ahead and clear out the messages so far. And let's take a look at our 2D array. So it's got 15 elements in it, and it starts out, and they just happen to be ordered 15, 14, 13. So the first one we come to is going to be the largest. So it's never going to get replaced. But it's not going to be the smallest. So we're going to replace this, replace this, replace this every time through with the smallest. And let's go ahead and in our watch window, let's see that occur as we step through the comparisons. So let's put a watch for lowest and highest. And just for fun, we can look at what the current element value is. Okay, and so let's go ahead and step through hitting F10 and watch our code operate. So lowest is set to 15, highest is also set to 15, and is element, which is for the first one 15 less than lowest, then we're going to change it. Well, it's not, so nothing happens. And is element greater than highest? Well, no, it happens to be set to highest, so no change there on the first time through. Okay, so what about the next one? Well, our lowest element is set to 15 and element is 14, so we're going to see that change. And we do. But highest, 14 is not greater than 15, so that is not going to change. As a matter of fact, it's not going to change for the rest of the elements we can compare. It's the lower one that's going to keep getting lower and lower. So let's watch as that happens. 13, 12, 11, 10, 9. So I'll slow down my keystrokes for a moment because the display wasn't keeping up. So you didn't see it in the video, but it went through 9, 8, 7, 6, 5, 4, 3, 2, 1, and we're going to run out of elements here, so we're done. And now let's switch over to our immediate window, and we can watch as the output is sent to the debug window. Lowest is 1, highest is 15, and our code is complete. Let's turn our attention now to another common task, and that is sorting arrays. One of the things I should say from the beginning is that the method I'm going to show you for sorting one-dimensional arrays will sort the array in place. That is to say, it's going to alter the order of your original array, and once that has been done, if there was anything important about the natural order of that array, or if the order of elements in that array corresponded in their order to any other thing, such as parallel arrays, a second array that had data in it. So for example, let's say we store one array with student ID numbers, and a second array we store the student names. If we were then to sort one array by the student names, it would change order and it would no longer correlate in order with the student ID number in the second array. You would never be able to match the two up again. So think about what you're doing. It may be important to make a copy of the array into yet another array and then sort the copy of the array rather than sorting the original. You may need to preserve the orders. Think about what you're doing before you jump on this. Okay, let me show you another really handy thing. Anytime you're trying to learn coding, and there's a feature in IntelliSense that allows you to insert code snippets. It's sort of like this remarkable bank of sample code that you can learn to use and leverage examples. I find it most useful when learning new stuff to see an example of something similar to what I want to do. Then I have, some guidance about, here's how I get started. So let me show you how you would find something on sorting arrays if you didn't know at all where to begin, other than, of course, you can always hit the internet and use Google and other search engines to try and find what you're looking for. But let's take a look at what's built right in here. So if I go into Edit and IntelliSense, and in IntelliSense, if I then choose on Insert Snippet, there are tons and tons of collections for different occasions, as it were, of code. So we're interested in not application code, not in code patterns, not in data per se, but we are interested in arrays. Where would we find arrays under this? So fundamentals, collections, data types. Well, arrays are a data type. Let's take a look here in fundamentals. And under fundamentals, it breaks it out to math, file system, data types, and collections and arrays. Well, there you are. Okay, so let's look in collections and arrays. And then what would you like to do with an array? And as we scroll down through here, we find there is a snippet for sort an array. Okay, so it's automatically pasted code from its library in here, and it's declared an array animals, and it is putting lion, turtle, and ostrich into that array on declaration, and then it's sorting them. And we presume, since it's a string array, that it's sorting it by alphabet, as alphabetical sort. So L, T, and S. So those should come out sorted in alphabetical order when we're done. Let's take a look at what this code actually does, and we'll see. So let's set a breakpoint before the code runs. We'll add it to the watch window and see what happens when the code runs. So let's go ahead and start. Tell it to go. And let's take a look at the animals array. And right now, animals array has nothing in it. So let's hit F10. Now animals has been initialized, lion, turtle, ostrich. And in this line, we're going to run this array sort function on it, F10. And now lion comes before ostrich, comes before turtle. Neat. Okay, so now we've got a sample. Let's see if we can use that sample on one of our arrays. Now, this was a string array. Will this also work on a numeric array? So we've already got a numeric array, my array, out there. And so let's say array.sort on my array. And let's set a break and run it and go. All right. And we'll get rid of the animals variable from the watch window. Let's put my array in here. And here's my array, 91210. And then let's go ahead and hit F10 to step over this line of code. And now it's 01129. Nice. Okay, so that's sorted it, and it's now in order ascending. What if we wanted it to sort in descending order? What would be the change there? Let's see if we can experimentally or exploratorily find that. So when we were creating this, so array sort, and do we find, I see something called reverse, but that's going to reverse the existing order. Do I see anything that's like a reverse sort or sort descending? No. So if I say sort, let's look at the function prototypes and see if we can find where there is an option here. We'll look at the different variations on this declaration. So keys as array items, not quite what we're looking for. Array as array comparer, and there's the comparison rule. So if we wanted to compare, on some criteria other than alphabetical or numeric, and there can be others, we might need a custom define those. Let's see, items as array comparer, index length, nope. Items arrays index. Haven't found it yet. All right, so what's our workaround? Well, once we have it sorted and we want it in the reverse order, could we do this? Let's give that a shot. Go. All right, so my array starting out 91210, F10 to step over, and that should sort it 01129, and F10 to put it in the reverse order. And so now it's sorted in descending. So again, the limitation here is that this works only on one-dimensional arrays. And so we can write code to sort multi-dimensional arrays. I'm going to defer that for another lesson because the different ways or methods and algorithms for sorting are many. They offer different advantages, and they also offer a rich opportunity to discuss the efficiencies of sorting, which is really important because often the size of the data, the amount of data that you are sorting, can have a profound effect on the time it takes for the CPU to complete the sort, depending on the efficiency of the algorithm that you use. So we're going to defer that discussion to a later time. But for getting array variables of one dimension sorted in here, we can use the array sort method. And if we need them sorted in descending order, we can use the reverse to quickly change the order of the array and have them in descending order. And of course, if we do the reverse of a reverse, it will be back in ascending order. The thing we need to remember is that once we have sorted in place, we lose the natural order. And so if there was any external dependency or correlation of the data, or if the data, in addition to being present in the array, had some particular meaning based on the order of it. So example, you have a number of people running a race, and you have entered them in the position which they finished the race, the winner, the second runner-up, the third runner-up, and so forth down the line. If you were to sort them, you're going to lose that inferred data. So think about what you're doing before you apply the sort and whether you need to preserve any of the relationship or data about the order that they were originally created in. Next, let's explore searching arrays. So I've added some code here that will search a one-dimensional array. I've first declared a integer variable search result and initialized it to -1. And we're going to search a numeric array here. And as we've found, for one-dimensional arrays, there are often really useful methods and properties of the one-dimensional array, and we can make use of that here. So into the search result variable, we're going to store the result of a call to the index of method on the array. And that takes two parameters. The first is the array you want to search, and second is the item you want to search on. So I've hard-coded that as 2. So we're going to search for the value 2 in that array. And if it finds it, it will update it. And if not, it's going to be left at the -1 value it was initialized to. And since I'm not using that array to store any negative values, that's kind of an indicator to me that it was not found. It was, if -1 is still in there, we didn't find the value we were seeking. Okay, and so then we just evaluate that result to give our message out in the debug window. So if the search result is -1, we tell you we didn't find it. And if the search result is anything else, we tell you it was found at location. And what we're putting here is not what we're seeking too. We already knew what we were seeking. We're putting the index where that result can be found. Okay, so let's go ahead and refresh our memory the array that we're searching was initialized with the values 91210, and so we should find the value 2. And let's go ahead and run this and see if that turns out to be the case. And so go, and it says the item was found at location 2. And let's prove that that is the case. So let's come over to the watch window and my array, and in 2 we see the value 2, 91210. All right, just to make sure that wasn't, because 2 and 2 is kind of confusing. Which is the index, which is the value? Did we really do that correctly? Well, let's search for 9, modify our code, and see what we get back. And I would encourage you to explore and experiment in this way with your code as well. The best way to answer a question is writing code. The second best way is Google. So use the best way whenever possible. Okay, so let's search for 9. And go. And our immediate window. So this run, I probably should have cleared that run first, but this run produced the second output, item found at location 0. So is 9 found at array element 0? Let's go over to the watch window, explore it out, and element 0 is indeed 9. What if we have not found the value we're seeking? So that array does not have the value, for instance, 8 in it. Let's go ahead and run that and go. And back in the immediate window, it says item not found in array, and that's what we expected. So woohoo, that all works real slick. But what if we want to search a multi-dimensional array? And again, also, as you've kind of come to expect, multi-dimensional arrays don't have all of the same properties and methods as the one-dimensional array object. They're a little bit more complex, and so Microsoft's kind of left it to us to implement the details there. So let's do this. Let's go ahead and comment out this code for the time being. And fortunately, we already know how to walk or traverse the array. So let's come down and uncomment this code that I've prepared, and then look and see what we're doing. So I have 2 for next loops, one nested in each other, which is 1 for each dimension. If it was a 3-dimensional array, we'd nest 3, and if it was a 4-dimensional array, 4, and so on. And so I'd previously declared I and j, and so I'm using a for next loop, and I want to go from the beginning of the array on the first dimension to the end of the array on the first dimension, and then within that I want to go and walk the array for each column. So on the 1 dimension, so on the 0 dimension from the beginning to the end, and on the 1 dimension from the beginning to the end. And rather than hard coding the dimensions of the array, I'm making the code get it for me, which makes it a more versatile piece of code. So we always expect that the get lower bound is going to be 0, but there can be some things we could be doing that would change that. We're not going to get into that now. It's a little more advanced utilization of collections and lists and arrays. So that's going to return, we expect, a 0, and this is going to return the number of columns, and this is going to return the number of rows, or reverse that rather, columns and then rows. And we're going to walk that and look for, in this case, the value Peter. And I could easily replace Peter here with a variable and then just assign or take a user input to say, what do you want to look for? So we're walking this down and we're looking at each element. So we're visiting each element in the array. Isn't there a better way to do it than having to check each element of the array? No, that's really what you have to do. You have to go, there's no magic. You have to go and see, is it really in there? And so even if it's a very large array, we're going to walk every element row by row, column by column. And so if Brady's IJ is Peter, then we're going to print that the element was found, okay? And doing it this way, if we were to find more than one Peter, since this will walk the entire, we'll get output a list everywhere we find it. In this case, we only expect to find Peter at one element. We can go look and see what was that. So Peter should be at the 1, 2 element. And let's see if that actually is indeed the case. Okay, so it's going to walk all the first dimension and all of the second dimension, looking element by element at the ij element, and if and when it finds what we're seeking, in this case Peter, it's going to give us a message, and it'll say Peter found an element. We hope that says 1, 2. So let's run that and see if that's what we expect, if that does what we expect. I'm going to come over here for a second and clear that and come back to the running program, tell it go. It hits the breakpoint, and there it is. Peter found at element 1, 2. And if we come over here and let's get rid of the watch on my array, and let's put a watch in on Brady's. And yep, the 1, 2 element is Peter. So let's double check that, and let's say we're looking for Dad. And let's run that. And again, I'm come back over to the immediate window and clear that before the run. And go. And the Dad element is found at 2, 1. And again, does that match? Yep. So that matches what we were expecting. Dad at 2, 1. And there it is. And then let's look for Sam the Butcher. Now, Sam the Butcher is not listed in the immediate Brady family, so nothing should be output in this case. Look for Sam, and if we do find Sam in there, Sam found an element, whatever, and let's run it. And again, let's clear the immediate window, back to the program, and go. And nothing is output because we only said print if you found something, and we didn't put any logic in for giving us a message if it wasn't found. Let's do one other thing, and that is let's monkey with it and see what happens with this code if we were to have 2 hits on the thing we're searching for. So we're looking for Sam. Let's go ahead and change Brady's 1, 2 equals Sam. And let's change Brady's 0, 1 also equals Sam. And now let's stop this and restart it. And back to the immediate window. The immediate window is clear. We didn't have anything in there. So back to our code and go. And we found Sam at 0, 1. And we found Sam also at 1, 2. And let's see, does that jive with the reality? So here's our modified array. Sam at 0, 1. And Sam at 1, 2. Sam at 0, 1. Sam at 1, 2. And so that's working. So really there's no rocket science here. We just took what we had already learned about using for next loops to traverse the array, and we traversed it. And in the traversing each element, we looked for the thing we were searching for, and so pretty nifty. And the other thing that I like about this example is rather than hard coding the dimensions of the array, we made it dynamically determine the dimensions, and that's going to be more flexible code and won't break if somebody redimensions the array that we're searching to a different size, or if we want to use that code on a different array, modifying it would be pretty simple, and we'd be able to have that code just basically work. All right, so I think we'll leave it here for now. This concludes the lesson.